Last October, researchers asked a major AI assistant a simple health question: should I be worried about the bird flu? It answered instantly, confidently, citing a news article from 2006, 20 years stale. And in that same study, 45% of AI answers to news questions contained at least one significant error. Here's the uncomfortable part. The model didn't malfunction. It did exactly what it was built to do. And if you're shipping anything on top of a language model, this failure is sitting in your product right now. There is a fix. It's called Retrieval-Augmented Generation, RAG. And by the end of this video, you'll know how it works, where it breaks, and how the people who do this well actually build it. Here's the route. Chapter 1. Why we need RAG at all. Chapter 2. What RAG actually is. Chapter 3. The core pipeline, end-to-end, chunking, embeddings, vector search, and how it all lands in the prompt. Chapter 4. Where naive RAG breaks, including a famous statistic that turns out to be made up. Chapter 5. The fixes that make up today's production standard. Chapter 6. The advanced stuff, graphs, agents, multimodal routing. And Chapter 7. How to measure any of this, and the trap almost everyone falls into. Let's go. Chapter 1. Why we need RAG. In this chapter, we will walk through 4 things. 1. The frozen knowledge problem. 2. The 3 symptoms it causes. 3. Why fine-tuning does not fix it. And 4. Why a million token context window does not fix it either. Section 1.1. Frozen knowledge. A language model is not a window onto the world. It's a photograph of it. Training ends on some date, the weights freeze, and everything after that date simply does not exist inside the model. That's why the bird flu answer happened. The photo was taken when a 2006 vaccine trial was current news. And here's the misconception. Newer models have newer cutoffs, so this solves itself. No. The cutoff moves. The freeze is permanent. The model has no internal signal that its knowledge is stale. It will report a 20-year-old fact with exactly the same confidence as yesterday's. Confidence and currency are completely decoupled. Keep that sentence. The whole chapter hangs on it. Section 1.2. The symptoms. Frozen knowledge shows up 3 ways. 1. Hallucination. The model fills gaps with fluent fiction. Stanford measured general-purpose models on real legal questions. They hallucinated on 58 to 88% of them. 2. Outdated answers. Technically true in a year that's gone. 3. And this is the one that kills enterprise projects. Your private data. Your warranty policies, your runbooks, your spec sheets. The model has never seen them. Ask it about your company and it can only improvise. Now, the good news. Ground those same models in real documents and the errors collapse. Not to 0. A grounded model can still misread the page it was handed, but most of the failure simply disappears. And here's the part that matters. Nothing about the model changed. Same weights, same training. One architectural change. Section 1.3. Why not fine-tune? The obvious counter. Just fine-tune the model on our documents. This is the most expensive misconception in applied AI. Fine-tuning is superb at teaching behavior. Tone, format, following your conventions. It is terrible at adding facts. And researchers have measured why. When you fine-tune on genuinely new knowledge, the model learns it slowly and reluctantly. And as it finally memorizes the new facts, something ugly happens. It starts hallucinating more on everything else. Teaching it new facts literally teaches it to make things up. And even if it worked, think about the operations. Every knowledge update means another training run. Hours to days of waiting, real money burned, and a fresh model to validate and redeploy. Your prices changed this morning. Fine-tuning shapes how the model talks. It cannot keep up with what is true. Section 1.4. Why not a giant context window? Second counter. Context windows are huge now. Just paste everything in. 2 problems: recall and economics. Recall first. Here's a question. Does the manual mention Aqua Shield coding? Easy. The words in the question are the words on the page. Simple string matching. The model nails this at any size. And that's the demo you've seen in every launch video. But real questions don't quote the document. A writer asks, is the battery protected against rain? The answer is that same Aqua Shield sentence. And now, not a single word matches. The model has to connect meaning to meaning, and that connection is exactly what weakens as the context grows. The page is in the window. It just stops being seen, especially in the middle. That's the part no launch demo shows you. Then the economics. A giant context means shipping the entire library to the model on every single question. You pay for every page, every time, and the answer arrives slower. Retrieval sends 3 relevant pages instead. Long context is a wonderful tool. It is not a knowledge strategy. Let's recap on why we need RAG. If you remember 3 things, make it these. 1. A model's knowledge is frozen at training time, and it will not warn you it's stale. 2. Fine-tuning changes behavior, not knowledge. It cannot reliably teach new facts. 3. A bigger context window is not a knowledge strategy. Recall, degrades, and you pay for every token. So, fresh, private, reliable knowledge must come from outside the model. That is retrieval. Chapter 2. What RAG actually is. In this chapter, we will walk through 4 things. 1. The definition in 1 sentence. 2. The 2 halves of every RAG system. 3. The analogy that makes it stick. And 4. Why grounding creates something a raw large language model can never give you: trust. Section 2.1. The definition. Retrieval-Augmented Generation. Before the large language model answers, the system retrieves relevant documents from an external source, and the LLM generates its answer grounded on what was retrieved. In plain terms, the model gets to look things up before it speaks. That's it. That's the whole idea. Coined in 2020 by Patrick Lewis and colleagues at Facebook AI Research, and their stated reasons are worth quoting because they predicted this whole video. Provenance. You can see where every answer comes from. Simply put, answers with receipts. Inspectability. You can audit exactly what the LLM saw. And updatability. Quote, the memory can be updated as the world changes. No retraining. The paper called external documents a second kind of memory, which brings us to the architecture. Section 2.2. 2 halves, 2 memories. Memory 1. Parametric. Everything baked into the large language model's weights during training. In plain terms, what the model knows by heart. Insanely expensive to write, instant to read, and impossible to edit. You cannot reach into the weights and fix a price. Memory 2. Non-parametric. An external index you control. In plain terms, a bookshelf the model can look things up on. Cheap to write, editable line by line, inspectable. RAG wires the second memory into the first at inference time. Inference time simply means the moment a question is asked. And that gives you the 2 components every RAG system has. The retriever, its only job is deciding what's relevant, and the generator, the large language model itself, whose job is deciding what to say about it. Keep those responsibilities separate in your head. When RAG fails, the first diagnostic question is always, which half failed? Section 2.3. The analogy. The classic one. A raw large language model is a student taking a closed book exam, answering from whatever it memorized. RAG makes the exam open book. Good start, but here's the version that earns its place. RAG is a brilliant professor who has never read your company's documents. Plus, a librarian. The librarian fetches the exact page, The professor reads it and answers. 2 characters, because that's the architecture you just met. The librarian is the retriever, the search half. The professor is the generator, the LLM itself. And notice what changed. The professor's job is no longer to know the answer. It's to read the answer and present it well. Hold on to both characters because each one fails in its own way. Section 2.4. Grounding and why it buys trust. Ask a raw large language model. Why did you say that? The honest answer is, it was somewhere in my training data. Ask a RAG system the same question, and it points at a page. That is grounding. In engineering terms, the LLM's answer is constrained to the documents retrieved for this question. In plain terms, the model answers with the page open in front of it. Here's our example for the rest of this video. Voltride, an e-bike company, building an assistant over its manuals, policies, spec sheets, and support tickets. A customer asks, "Does water damage void the battery warranty?" A grounded answer comes back, citing the warranty policy, page 4. That pointer changes everything. Users can verify, auditors can trace, and cited answers measurably score higher on credibility with expert users. One caution, and it matters. A citation makes an answer verifiable, not verified. An LLM can cite a real page that does not say what the model claims. Trust the pointer. Still, check the page. Let's recap on what RAG actually is. If you remember 3 things, make it these. 1. RAG means 2 memories. The large language model's weights and an external index you can edit anytime. 2. The retriever finds, the generator reads. When something breaks, diagnose them separately. 3. Grounded answers point at a page. That makes them verifiable. Not automatically true. Chapter 3. The core pipeline. This is the heart of the video. We will walk through 5 things. 1. Chunking, cutting documents into retrievable pieces. 2. Embeddings, turning text into geometry. 3. The vector database. 4. Retrieval at query time. And 5. How it all lands in the prompt. We will follow one question through the entire machine. Section 3.1. Chunking. Before anything gets retrieved, documents get cut into pieces. Because you retrieve pieces, not files. In plain terms, chunking decides what a page is. For the librarian, and how you cut matters more than almost anyone expects. Cut blindly, fixed size, every 500 characters, and you slice sentences mid-thought and tables mid-row. The retriever can only find what the cut left whole. The production default chunks around 400 to 500 tokens, cut by a recursive splitter. In engineering terms, it tries paragraph breaks first, then sentences, then words. In plain terms, it cuts where a human would pause. Splitters that understand document structure go further. Headings stay with their sections, and tables travel whole. Overlap between chunks, 10 to 20%, is the folklore, but when researchers measured it systematically, they found no reliable retrieval benefit. So, convention, not law. Measure it on your own data. Let's make that concrete. Here's a full page from Voltride's warranty doc. Headings, paragraphs, and a coverage table. Same page every time. Watch where each method cuts it. Method 1. Fixed size. The blade falls every n characters, wherever that happens to be. Look at the damage. One cut breaks a sentence in half. The next one splits the table between its rows. Those pieces are half thoughts now. Method 2. The recursive splitter. Before cutting, it backs up to the nearest paragraph or sentence boundary. Every piece now reads cleanly. But look at the last cut. The table got separated from the sentence that explains it. Method 3 cuts along the document structure. It sees the headings, the paragraphs, and the tables. The heading stays with its section, and the table travels with the sentence that introduces it. Every chunk is a complete thought. And Method 4, semantic chunking. No markup needed. It measures sentence by sentence where the topic shifts and cuts there. Notice, it found nearly the same boundaries. Good structure and real meaning usually agree. The principle underneath all of it: every chunk should be a self-contained thought. If a human cannot understand it alone, neither can the retriever. Section 3.2. Embeddings. Now, each chunk becomes a vector, a long list of numbers, typically 1,000 to 3,000 of them, produced by an embedding model. That is a separate, much smaller model than the LLM itself. And here is the intuition, the most important one in this whole video. An embedding is a location on a map where distance means meaning. Watch, take a leisurely walk in the woods. Enjoy a stroll outside. Not one meaningful word in common. A keyword search scores them 0. Their embeddings land side by side. That is the superpower, retrieval by meaning, not by matching. Closeness on the map is measured with cosine similarity. In engineering terms, the angle between two vectors. In plain terms, a score where higher means more similar, and the cost? Almost negligible, cents per million tokens, with open models near the top of the leaderboards. One thing to hold on to: this map is built from meaning, and only from meaning. Keep that loaded. Section 3.3. The vector database. Every chunk is now a point on the meaning map. A real product has millions of them, and every single question comes down to one job: find the points nearest to this one, fast. The obvious way is to compare the query against every stored vector, one by one. At 1,000,000 vectors, that brute force scan takes most of a second. For one user, asking one question, production traffic would bury it. So real systems search the map the way you drive across a city. Take the highway first. Long jumps, few exits. When you're roughly in the right neighborhood, take an exit onto smaller roads and refine. And finally, walk the last block to the exact address. That is exactly how the standard index works. It is called HNSW, and it stacks the map into layers. The top layer holds just a few landmarks, connected by long-range links. The query enters there, jumps from landmark to landmark toward its target, then drops into denser and denser layers, refining as it goes, until it lands on the true neighbors. The result: the same million vector search now takes just a few milliseconds, and it still finds 95 to 99% of the true nearest neighbors. You trade a sliver of recall, and the search runs about 100 times faster. That trade is what makes semantic search practical at all. And a reality check before you reach for a dedicated vector database. One team indexed all of Wikipedia this way, 144 million chunks, and queries come back within a screen refresh. At a few million vectors, plain Postgres with the PG vector extension keeps up fine. Boring choice, correct choice. Section 3.4. Retrieval at query time. Everything so far happened offline while indexing. Now a customer shows up and asks, "Does water damage void the battery warranty?" The question gets embedded too. Same embedding model as the documents, always. Otherwise, the two geometries simply do not align, and it lands as a new point on the same map. The system pulls the nearest chunks to that point. This is called top K retrieval, and K is just how many you take. Production defaults sit between 5 and 10. Some systems fetch a wider set, 20 to 50, and refine it in a second pass. Now, two honest footnotes about those similarity scores. First, the scores are relative, not absolute. 0.6 can be an excellent match for one embedding model, and a mediocre one for another. The score ranks this list. It is not a grade. There is no universal threshold for a good match. Second, and this one is sneakier, similar is not the same as useful. Watch. A chunk that merely restates the question, customers often ask whether water damage voids the battery warranty, sits extremely close to the query on the map, closer than the paragraph that actually answers it. Nearest in meaning is not most helpful. And notice, the large language model has not been involved yet. All of this happens before the LLM reads a single word. Naive RAG stops right here. Take the top 5, hand them over, move on. Remember the trap it just walked past. Section 3.5. Into the prompt. This is where the two halves meet. The retrieved chunks get pasted into a prompt template, wrapped around the question. That is the augmented in Retrieval-Augmented Generation. In plain terms, we hand the professor the pages, stapled to the question, and the details of that template are load-bearing. Detail 1. The instruction says, answer only using the context below. That word only is what keeps the professor reading instead of improvising, and pair it with an escape hatch. If the context is not enough, say so. An honest, I do not know, beats a confident guess every time. Detail 2. Demand citations per claim by chunk ID. A vague, cite your sources, produces prose you cannot parse. Numbered chunks give you numbered receipts. Detail 3. The one everyone misses. Order. Large language models read a long context the way people skim. The start sticks, the end sticks, and the middle blurs. So put your best chunk first, your second best last, and never bury the winner in the middle of the stack. Then, the LLM finally reads and answers. Rain and splashes are covered. Full immersion voids the battery warranty. Source. Warranty policy, page 4. Grounded. Cited. Done. And that is the whole machine. Ingest offline. Then retrieve, assemble, generate. All of it in the blink between question and answer. Let's recap on the core pipeline. If you remember 3 things, make it these. 1. Chunks must be self-contained thoughts. Cut along the document's structure, because the retriever can only find what the cut left whole. 2. Embeddings turn meaning into geometry. Search finds the nearest points on that map. And remember, nearest is not always most useful. 3. The prompt is assembled evidence. Answer only from the context. Cite per claim, and put your best material first and last. Chapter 4. Where does naive RAG break? In this chapter, we will walk through 4 things. 1. What the failure data actually says, including a famous number that does not survive contact with its own source. 2. How chunking fails in practice. 3. The 2 very different ways retrieval misses. And 4. The exact match blind spot that every semantic system shares. Section 4.1. What actually fails? If you have read anything about RAG, you have met the claim that almost all RAG failures are retrieval failures. It usually arrives with a suspiciously precise percentage attached, so I went looking for the study behind it. And here is how the chase went. A blog cites a blog, which cites another blog, and the trail dead ends at a Medium post with no source at all. The number is folklore. Delete it. So what do peer-reviewed error analyses actually find? Honestly, a better story. Retrieval really is the largest single source of failures, consistently, study after study, but it is far from the only one. Generation, query understanding, and plain parsing all take their share of the blame. And here is the kicker that makes retrieval the thing to fix anyway. It is the bucket you can empty without touching the model. Anthropic measured this on their own pipeline. A well-built, embeddings-only setup still misses the answer a small but real fraction of the time. Stack the standard retrieval fixes on top, and most of those misses simply disappear, and all of the gain lands on the retrieval side. So the lesson is not the number. The lesson is when your RAG system is wrong, interrogate the librarian before you blame the professor. Section 4.2. Bad chunking, revisited, now with consequences. Ask Voltride's assistant, what is the Alpine X5's range at 25 degrees? Here is what happened under the hood. The spec table got chunked mid-row, headers in one chunk, values in another. So the retriever dutifully returns a chunk full of naked numbers, and the LLM staring at 340, 62, and 4.1 with no column names in sight, confidently reads out the wrong one. And here is the same disease in a worse strain. A policy sentence split at exactly the wrong place. Chunk 1 ends. Contractors follow the standard onboarding process. Chunk 2 begins. Unless engaged on a project under Annex B. That word, unless, carries the entire legal point, and it lives in a fragment that never gets retrieved together with its rule. Nothing downstream can fix this. Not a better model, not a better prompt. The information was destroyed at ingestion time, before anyone asked anything. And one counterintuitive result, before you overcorrect, fancy semantic chunking can lose, end-to-end, to the boring recursive splitter. Tiny perfect fragments retrieve beautifully and then starve the generator. So, respect structure, keep thoughts whole, and measure on your own data. Section 4.3. Recall versus ranking. When retrieval misses, it misses in two very different ways, and confusing them wastes engineering months. So let us pull them apart. Failure 1. Ranking. The winterization guide is in the index. It is relevant, and it sits at rank 12, while your cutoff is 5. The answer was in the building. It just never got upstairs. The cure is better ordering, retrieve wider, then re-rank. Failure 2. Recall. The document never made it into the index at all. A scanned PDF that did not parse. A page that did not survive chunking. The answer never even entered the building. And practitioner audits find this alarmingly often. In one brutal decomposition of financial document systems, retrieval usually found the right file and then missed the right page almost half the time. Right building, wrong floor. So, diagnose before you treat. If the answer is not in the index, no re-ranker on Earth can save you. Ask one question first. Was the answer even retrievable? Section 4.4. The exact match blind spot. A writer's display flashes error E4392. They ask the assistant, and here, a quick prediction. The index genuinely contains a document for this exact code. Does semantic search find it? Think about it for a second. Remember what embeddings do. They map meaning. So what does E4392 mean as language? Nothing. It is an arbitrary token. On the meaning map, it lands inside an error code-shaped blob, millimeters away from E4390 and E4401. So the retriever returns beautifully relevant documents about the wrong errors, plausible neighbors, wrong answer. And this is systematic. Part numbers, product codes, people's names, legal clause numbers, API routes. Everywhere precision lives in the literal string, search by meaning is structurally blind. The fix is almost embarrassing. Keyword search. The classic ranking algorithm, BM25, has been matching exact strings since the 90s. In plain terms, it finds the actual words, including strings no embedding model has ever seen. So, is the future of retrieval keyword search? No. It is both, working together. Let's recap on where naive RAG breaks. If you remember 3 things, make it these. 1. When RAG fails, check retrieval first. It is the largest failure bucket and the cheapest to fix. 2. Ranked too low and never indexed are different diseases with different cures. 3. Semantic search cannot see exact identifiers. Codes, names, and versions need keywords. Chapter 5. Improving Retrieval. The Sensible Default Stack. In this chapter, we will walk through 4 things. 1. Hybrid search. Vectors plus keywords, fused together. 2. Re-ranking. A second, smarter pass. 3. Fixing the query itself. And 4. Metadata. The unglamorous filter that solves problems embeddings never will. Section 5.1. Hybrid search. 1 query, 2 retrievers, running in parallel. The dense retriever searches by meaning. It returns beautifully relevant documents about the wrong error codes and buries the exact one we need at rank 9. The keyword retriever matches the literal string. E4392 is unmistakable, so the right document jumps straight to rank 1. Each side covers the other's blind spot. The question is, how do you merge two lists into one? The tempting answer is to average the scores. Don't. A keyword score of 14 and a cosine of 0.61 live on completely different scales. Averaging them is like adding a temperature to a phone number. You get a number. It means nothing. The standard answer is reciprocal rank fusion. Ignore the scores. Use only the positions. Every document earns a bonus from each list it appears in, and the bonus shrinks as the rank drops. Now watch it work on our document. Rank 9 on the meaning side, a small bonus. Rank 1 on the keyword side, the biggest bonus there is. Added together, that total beats every document that sat mid-table on both lists. So it climbs, from rank 9 to rank 1. No normalization, no tuning. Almost embarrassingly robust, which is exactly why it is built into every serious search engine. And Anthropic measured the impact on their own benchmark, adding the keyword signal cut retrieval failures roughly in half. Hybrid search is not an optimization. It is the floor. Section 5.2, Reranking. Fast retrieval has a built-in weakness. To stay fast, it never really reads anything. Every chunk was squeezed into a single vector before your question existed, and the query is squeezed the same way. Comparing those two summaries is enough to find the right neighborhood. It is not enough to get the order exactly right. A re-ranker fixes the order by doing the one thing the first pass skipped. It places the question and a chunk side by side and reads them together, word for word, scoring how well this exact text answers this exact question. Think of it as the difference between skimming titles and sitting down to actually read. Much more accurate, and much too slow to run on the whole index. So we run it only on the short list. Watch it happen. Fast retrieval hands back its best guesses. A page of winter writing tips sits right at the top, just because it sounds related. The guide that actually answers the question is stranded down at rank 4. Now the re-ranker reads each candidate in turn and scores it fresh. Writing tips, nice words, wrong topic, low score. The winterization guide, it answers the question head-on. Top score, and the whole list reorders. The real answer climbs to number 1. The imposter sinks to the bottom. That is the entire pattern. Cast a wide, cheap net, then read the finalists closely. Layered on top of hybrid search, this clears out most of the errors that were still slipping through. But respect the limit. A re-ranker can only reorder what retrieval already found. It cannot bring back a document that was never there. Recall problems stay fatal. Fix those upstream. Section 5.3. Fixing the query. So far, we assumed the query was fine. Often, it is not. A panicked customer types, "Bike dead after rain, question mark, question mark." That is nothing like the calm, formal language of the actual warranty policy. So before we even retrieve, we can use a language model to repair the query itself. There are 3 standard moves. Move 1. Rewrite. Turn the conversational mess into a clean search-shaped question. And in a chat, this is where you resolve the pronouns. If the user just says, "Is it covered?" the word it means nothing on its own. Rewriting pulls the real subject back in from the conversation, so retrieval is not left searching for the word it. Move 2. Multi-query. Instead of guessing the single best phrasing, generate several. Ask the model for a handful of ways to say the same thing. Retrieve for all of them and fuse the results. Different wordings catch different corners of the index that any single phrasing would miss. Move 3 is the clever one. It is called hide. Watch the logic. A short question and a full answer barely look alike, so the question sits far from the answer on the map. So HyDE flips it. Let the model write a fake, made-up answer first, and search with that instead. A hallucinated warranty paragraph lands right next to the real warranty paragraphs. You are probing answer space with an answer-shaped probe. One honest update on HyDE: it is no longer a default. It became a targeted tool because hybrid search and reranking already recover most of what it used to add, and the rule under all three: query transformation reshapes the probe. It cannot recover information that was destroyed back at ingestion. Section 5.4. Metadata and filtering. This last one is unglamorous, and it solves a whole class of problems that embeddings simply cannot touch. Our spine question, one more time: does water damage void the battery warranty? Here's the catch. Voltride's index holds two versions of that policy. The old one says water damage voids the warranty. The current one says it is covered. Same question, two opposite answers, both sitting in the index. And here is the trap. Those two documents are almost word for word identical, so their embeddings are nearly the same point on the map. Which version wins the similarity race is basically a coin flip, and no embedding model will ever fix this, because recency is not a property of meaning. It is a property of the record. So, you fix it outside the vector. Store structured fields right next to every chunk: its source, its date, its section, its page. Then filter before you search. Keep only the current policy, and the stale one is not outranked. It is simply not in the race. In plain terms, meaning finds the right topic, metadata enforces the hard rules. And that exact same mechanism gives you tenant isolation and permissions. Never retrieve a document this user is not allowed to see. And because the page number rides along in the metadata, it is what powers a real citation. So, dense vectors, sparse keywords, and metadata filters. Three signals working together. That is the modern retrieval stack. Let's recap on the production stack. If you remember three things, make it these. 1. Production retrieval is hybrid, meaning plus keywords fused by rank, so exact codes and fuzzy questions both land. 2. Retrieve wide, then re-rank narrow. One slow, careful pass over a cheap shortlist, and the right answer climbs to the top. 3. Fix the query before you search, and let metadata decide what meaning cannot. Dates, versions, and permissions. Chapter 6. The Advanced Architectures. Think of this as the expensive aisle of RAG. Powerful tools, each with a real cost. So the skill here is knowing when each one actually earns it. In this chapter, we will walk through four things. 1. GraphRAG, for when the answer lives in the connections between facts and not inside any single document. 2. Agentic RAG, where the system decides for itself what to look up and when to stop. 3. Multimodal RAG, for when the answer is a picture, not a paragraph. And 4. Adaptive routing, the piece that quietly keeps all of this affordable. Section 6.1. GraphRAG. Ask Voltride's assistant a harder question. Which suppliers provided the cells for the recalled battery batch? Vector search does its best. It returns some chunks about suppliers and some chunks about the recall. But notice the problem. The answer is not sitting inside any single chunk. It lives in the connection between three separate documents, and plain similarity search has no way to follow a connection. GraphRAG from Microsoft Research is built for exactly this. First, a language model reads the whole corpus and pulls out the key entities and the relationships between them. It stores all of that as a knowledge graph. Then, it clusters the graph into communities of related ideas and writes a summary for each one. Now, the queries get interesting. A relationship question walks the edges of the graph, one hop at a time, to assemble its answer. And a broad, corpus-wide question like, what are the recurring failure themes this year? That one reads the pre-written community summaries instead. On exactly those big picture questions, GraphRAG clearly outperforms plain vector search. Now, the honest part, cost. In its early days, building the graph was brutally expensive because it ran a language model across your entire corpus up front. But newer variants, like Lazy GraphRAG and LightRAG, cut that cost dramatically by deferring most of the model work until a question is actually asked. So cost is no longer the real objection. Complexity is. So here's the rule. If your questions genuinely traverse relationships, think supply chains, case files, org charts, then build the graph. But if your corpus is just a pile of topic-siloed policies, then plain vector RAG was never your problem in the first place. Section 6.2. Agentic RAG. Everything so far has been a fixed pipeline. The query takes the same path every single time, and the first retrieval is the only retrieval. Agentic RAG hands the model the steering wheel. Now it decides, should I even retrieve? What exactly should I search for? And the crucial one, is what came back actually good enough? Or do I need to try again? Take a real question. Why did returns spike after the March firmware update? No single search can answer that, so the agent breaks it apart. One search for the returns data around March, another for the firmware changelog, and a third for support tickets that mention the update. It plans its own investigation. Then, it does something a fixed pipeline never does. It reads its own results and grades them. A lightweight judge asks, is this evidence actually strong enough? Where the evidence is thin, it goes back and searches again. It loops, retrieve, check, refine, and only when it is satisfied does it finally write the answer. But that power is not free. Each loop is another round of retrieval and another model call, so an agentic query is noticeably slower and far more expensive than a single-shot lookup. You are paying in time and in tokens for the system to actually think. So the discipline is simple. Put a hard ceiling on the loops so it can never spiral. Let it exit early, the moment the judge is satisfied. And most importantly, do not send every query down this expensive path. A simple question should still take the simple road. Section 6.3. Multimodal RAG. A technician asks a simple question. Which connector goes to the brake sensor? The answer absolutely exists, but it exists inside a wiring diagram. It is pixels, not words. And text only, RAG threw that diagram away at ingestion time, along with every chart in every report you own. There are 3 tiers of fix in rising order of power. Tier 1, caption everything. A vision model looks at each image and writes a text description of it, and you index those descriptions. It is cheap, and it reuses your entire existing pipeline, but it quietly loses detail. Tier 2, unified embeddings. These are models that map text and images into one shared space, so a text query can land right next to a diagram directly, with nothing translated into words in between. Tier 3 is the current frontier, and it is elegant. Skip the extraction entirely. Render each PDF page as an image. Embed that image as a grid of small patches, and match the words in the query to the regions of the page. This is the ColPali family. There is no OCR step to fail. No table extractor to lose a row. The page you see is the page it searches. Now, the trade-offs. This power costs you far more vectors, so you pool them coarsely and re-rank finely. And here is the #1 operational risk. It is not the retriever, it is the generator. Vision models can confidently misrate a chart, so before you trust it, build a chart quiz from your own documents and measure it. Section 6.4. Adaptive routing. This is the least glamorous idea in the whole chapter, and it is the one that makes everything else affordable. Watch what happens when 3 very different queries hit your assistant. The first one is just, thanks. That needs no retrieval at all. The second, How long is the battery warranty? That is one cheap single lookup. And the third, why did returns spike in March? That one needs the full agentic loop. Now, if you send all three down the same path, you lose either way. Route everything through the heavy agent, and you are massively overpaying for a thank you. Route everything through a single lookup, and the hard question gets a shallow, wrong answer. So you put a tiny, fast classifier right at the front door. It reads each query and picks the path. No retrieval, a single lookup, or the full loop. In plain terms, it is a bouncer, sending each question to the right room. A small model does this almost instantly and very accurately. And the payoff is not just lower cost. Accuracy actually goes up, because now every query gets exactly the machinery it needs, and no more. The one risk to respect is the router mistaking a hard question for an easy one. So you stay conservative and you escalate whenever the answer comes back with low confidence. Routing is the cheapest technique in this entire video, and it is the one that lets you actually afford the expensive aisle. Let's recap on the advanced architectures. If you remember three things, make it these. 1. Graphs answer the questions that live in the relationships between documents, not inside any single one. 2. Agents decide for themselves what to retrieve, and they check their own evidence. That power is real, but so is the cost. 3. Treating a page as an image reads exactly what text extraction throws away, and underneath all of it, a small router keeps the whole system affordable. Chapter 7. Evaluation and the Trap. In this chapter, we will walk through three things. 1. The handful of numbers that tell you which half of your system is actually lying to you. 2. The real trap, and it is not what you would expect. It is not under engineering. And 3. The single rule that everything in this video has been quietly building toward. Section 7.1. Measure or you are blind. Voltride's assistant confidently tells a customer, your battery warranty lasts 5 years, but the actual policy says 2, so the bot is wrong. The real question is, where did it go wrong? Was it the librarian or the professor? To answer that, RAG evaluation breaks the score into 4 separate numbers. The standard vocabulary here is a framework called RAGAS, and the 4 numbers split cleanly into 2 teams. 2 of them grade the retriever, and 2 grade the generator. First, the 2 that grade the librarian. Context recall asks, did the chunks we pulled back actually contain the answer? And context precision asks, was that answer ranked near the top or buried under noise? In plain terms, did we find the right page and did we put it on top? Then, the 2 that grade the professor. Faithfulness asks, is every claim in the answer actually supported by the retrieved text? That is your direct hallucination detector. And answer relevancy asks the simplest question of all. Did it actually answer what the user asked? Now watch how this pinpoints the bug. If the correct 2-year policy was retrieved, but the model still said 5, faithfulness drops. It is a generation problem. But if that policy chunk never arrived at all, context recall drops instead. That is a retrieval problem, and no amount of prompt tuning will ever fix it. 2 honest caveats. These 4 scores are themselves judged by a language model, so calibrate them against a batch of hand-labeled examples before you trust any threshold. And remember what a score is really for. It is a diagnosis, not a grade. Its only job is to point at the broken half. Section 7.2. The real trap? Here's the thing that nobody selling you RAG tooling will ever admit. The failure mode that actually kills real projects is not being too simple. It is being too clever. The pattern repeats everywhere. A team proudly ships a knowledge graph, a multi-step agent loop, and multimodal everything. For a support bot whose single most common question is, what is the parental leave policy? The result? Painfully slow answers, a huge jump in cost per query, and accuracy that is no better than before, because their actual failures were mundane, chopped up tables, a few missed keywords, the kind of thing a single day of hybrid search and re-ranking would have quietly solved, now dressed up as a deep architecture problem. The engineers who do this really well are basically unanimous about it, and I will quote one of them directly: prioritize implemented value over implemented trends. So here is the discipline. Every single advanced technique has to earn its complexity against a specific measured failure that it uniquely fixes. Use a graph when your evaluations prove you have traversal questions. Reach for agents when your logs are genuinely full of multi-step ones. Go multimodal when the answers really do live in the pictures. Otherwise, you are just paying compound interest in latency, in cost, and in debugging headaches on capability that you cannot even name. Section 7.3. The rule. Honestly, everything in this entire video compresses down to just 3 moves. Here's the first. Build the boring stack, and build it well. That means chunking that respects document structure, hybrid search, and a re-ranker on top. This unglamorous setup quietly removes most of your retrieval failures before you have done anything exotic at all. It costs you almost nothing. Move 2. Build a golden dataset. A set of real questions from your own corpus, each paired with a verified correct answer. Then wire up the 4 gauges against it. This is hours of work, not weeks, and it quietly converts every future argument about architecture into a simple reading off a dashboard. And move 3, the one that ties the whole video together. Only add complexity when a metric names the failure. Is context, recall low, specifically on relationship questions? Now GraphRAG is a fix, not a fashion. Are multi-source questions the ones failing? Now an agent has earned its tokens. Because that, in the end, is the one thing that separates the teams whose RAG actually works from the teams with very impressive diagrams. They can point at the exact number that made them build each piece. Let's recap on evaluation and the trap. If you remember 3 things, make it these. 1, 2, metrics grade the retriever, and 2 grade the generator. That split alone tells you which half of the system is broken. 2, build a golden dataset before you build features. If you cannot measure it, you are only guessing. And 3, start with the boring stack and add complexity only when a measured failure actually demands it. Okay, let's lock the whole thing in from the top. The problem. A language model is a photograph, not a window. Its knowledge is frozen, its confidence is not, and it has never once seen your private data. Fine-tuning changes its style, not its facts. And a giant context window is a tool, not a knowledge strategy. The idea: give the model a second memory. Retrieve the relevant context. Generate an answer grounded on it, and cite the exact page, a librarian to find it, and a professor to explain it. The pipeline: chunk your documents with respect for their structure. Embed that meaning into geometry. Index it for fast, approximate search. Then retrieve wide, and assemble the prompt with your best evidence placed first and last. Where it breaks, almost always in retrieval. Destroyed tables, the right answer buried at rank 12, and semantic search going completely blind to an exact error code. The fix: the production stack. Hybrid search, a re-ranker, a rewrite of the query, and a hard filter on metadata. The expensive aisle: graphs, agents, and multimodal. All of it kept behind a router, and none of it added until a measured failure actually demands it. And holding all of it together, the one rule: build the boring stack first. Build a golden set to measure it, and let the metrics, not the trends, buy every piece of complexity you add. That's RAG, not the demo, not the trend chasing, but the way it's actually built. And that's a wrap for today. I really hope RAG finally clicked. If it helped, a like tells me to keep making these. A share sends it to someone who needs it. Subscribe, if you want the next deep dive. And in the comments, tell me what to build next.